Hello again, this is the third video and the last video in this series on normal distribution, z-scores, confidence intervals, standard error of the mean, t-distributions. And so we're going to talk about t-distributions now. So to lead into that, let's see where we've come to. So one of the real points is statistics. You have a sample of data from a population, and from that you can calculate a mean and a standard deviation for your sample. If you want to estimate the mean of the population from which you drew the sample, which is one of the things we like to do in stats, your single best point estimate is certainly the mean of the sample. You got a sample, you got a mean, and that's probably the population mean. But you know that it's probably not exactly that value, so you create a confidence interval, which means that I'm about 95% certain that the true population mean is in this window of values. And a confidence interval is a range of values which centered around the sample mean, calculated using the sample variability, that's likely to include the population of the mean from which the sample was drawn. Confidence intervals are dependent on two things. One is the sample size, and the other is the sample variability. Now, we've talked about the variability before and how you use the variability, the standard deviation of the sample, to estimate the standard error of the mean and what that's doing theoretically. Now we're going to talk about the influence of sample size. Why? Because most of the time you don't have a sample that's huge. If you have a sample that's huge, a large sample size of more than 130, for example, or 120, whatever, you can simply estimate the standard error of the mean from the sample and multiply that times 1.96, and that's your 95% confidence interval. But if you have a smaller sample size, you cannot use that SEM times 1.96. And we'll try to show you why. If you have a smaller sample size, you have to use a t-distribution. And so now we're going to talk about t-distributions. We're talking about t-distributions, and as I said before, the distribution of sample means, different sample sizes, and we're going to talk a little bit about t-distributions versus the normal curve. We won't talk about Gossett very much in this video. So when the sample size is greater than 120 or greater than 130, the normal curve pretty much is a good way to do this distribution of sample means. But if we go back to that hypothetical distribution of sample means, if the sample size is less than 120, it's not a normal curve anymore. Let me ask you a couple of questions. So, if you're going to take an exam in your biostats, do you want to come in and have me say, I'm going to write 2 questions? Or do you want me to come in and say, I'm going to write 5 questions for every hour? So you're going to have 20 questions for the total exam. Or do you want 2 questions total? Almost everybody's going to pick the larger number of questions. Why? Because the impact of one single missed question is diminished when the sample size is bigger. When the sample size is small, that occasional outlier example, like, oh, I know so much of this stuff, but I just didn't know that one thing he asked, is disproportionately emphasized. So you want to use a bigger sample because it's a better representation. Another analogy, sports teams. Outside of football, most sports teams, hockey, baseball, basketball, the professional teams have best of 7 playoffs rather than a single game championship. Why do they do that? Well, for revenue. I mean, you can, if you have a 7-game series, you can fill up the stadium 7 times and sell 7 times the amount of beer and all those kind of commercials and all that kind of stuff. But the other issue is, it's probably more representative when they have a 7-game series. In a single 1-game series, like the Super Bowl, if one player has a particularly bad or a particularly good game, it can inordinately affect the outcome of the championship. You can have one amazing player hit 4 home runs, well, it's never happened, but hit 4 home runs in one World Series game, and their team can still go on to lose the World Series 4-2. But in the Super Bowl, the one-timer event, one single outstanding play or series of plays can affect the overall outcome much more so. And this is sort of an example of the distribution of sample means in the normal curve versus the t-distribution. When I ask you if you want 50 questions or only 2, you're saying, if it's a 50-question exam and there's 1 or maybe 2 that I just didn't get for whatever reason, I'm not very much penalized because I know the other 48 or 49. If it's only a 2-question quiz or exam and I happen to ask one of the ones that you don't know, you're going to say, oh man, that's not fair. But I knew so much. It's not reflecting of my real understanding. Small sample sizes can sometimes be inordinately affected by outlier values. And that's what the t-distribution is all about. Sometimes when the sample size, the small sample size is not representative. And this is sort of a graphic depiction of that. This is probably not the best normal curve in the world, but this is basically a normal curve, the top one. And if this is the mean, if this is the standard deviation, you've got your inflection point, you get your 34% on the one side of the standard deviation, one standard deviation on either side of the mean, kind of a thing. This is a t-distribution where the sample size is closer to 30. This is a t-distribution when the sample size is even smaller. And all that's doing is this is the distribution of sample means. Remember, in the distribution of sample means, if you have a large sample size, more than 120 or whatever, you're going to have a normal curve. But if the sample size gets smaller and smaller, the distribution of sample means is not going to be normal anymore, because it's going to be more and more influenced, likely to be influenced by 1 or 2 more outlier values. And so you're more and more likely to get values that are out here at the high end that you wouldn't get with the normal curve. In essence, when you move from a large sample size, large as 120, 130 kind of a thing, if you move to 50, to 30, to 20, to 10, the distribution of sample means is no longer a normal curve. It is flatter, has a lower mean, and fatter. It has more values out there in the wings than a normal curve. And if what we're trying to do with this distribution of sample means is we're using this to predict the confidence interval, when it's a normal curve, one standard deviation on either side of this distribution will capture 68% of the data. If it's a t-distribution here, one standard deviation doesn't capture as much because there's more stuff on the outside. If it's a t-distribution with an even smaller n, one standard deviation captures even less and less. And the whole point of this is that if what you're trying to do by calculating a confidence interval is give me a range of values centered around the mean where you are 95% confident that you captured the population mean. If it's a normal curve, you'll move out 1.96 standard deviations out here, and you've got it. If it's a t-distribution which is flatter and fatter, if you move only 1.96 standard deviations out there, you've left a lot of data on the wings. You haven't captured 95%. You have to go higher than 1.96. If the distribution is from sample sizes of 30 or smaller, it's even further and further out there. And so in order to accommodate for the effect of sample size on this distribution of sample means, and this is what we're really trying to do when we're estimating the sample error of the mean, and we're going to calculate a confidence interval. When the sample size gets smaller, you cannot use data from the normal curve as your mathematical predictor. You have to use something else, and those are called the t-distributions. So this is, again, this is a normal curve, normal curve, where you use the z-scores. If you go 1.96 units out there, that's 95% of those values. in order to capture 95% of the values from a t-distribution with n equals 12, that actually has 11 degrees of freedom, n minus 1, you have to actually go out to 2.20, and there is where you capture 95% of the values on the purple curve, from this point to that point. On the blue curve, you go 1.96 and you capture 95%. And where did that value of 2.20 come from? We'll go to the next page. It comes from this. This is kind of hard to see, but this is just a copy of a t-distribution. And basically it says critical values per 0.05, and this is for different distributions of hypothetical sample mean values. Again, if it's a large sample size and you take a bunch of sample means, the distribution of sample means you will get 0.05% at 1.96. That's infinity there. It says 120. 120 to infinity, no matter how big the sample size is, if it's over 120 or so, your critical value in the t-table is 1.96, which is your value from your normal curve. It's the value from the z-table. When the sample size is very large, 1.96 standard deviation units from the mean in the distribution of sample means will capture 95% of the values from 1.96 above and 1.96 below. If you want to capture that same 95% of the value, if the sample size is 12, you have 11 degrees of freedom. I don't know if you can read this on the video, but it says 2.20. So you have to move not 1.96. You have to move 2.20 standard deviation units from the mean on that distribution of sample means. 2.20 standard deviation units on either side, and that, with a sample size of 12, with 11 degrees of freedom, will capture your 95% confidence interval. And so the point of this is that as the sample size changes, the hypothetical distribution of sample means will change with it. If the sample size is 120, 130 or greater, the distribution of sample means will always match the normal curve, and 1.96 times the standard error of the mean will be essentially how you calculate your 95% confidence interval. If the sample size becomes smaller than 120, you move further and further away from the normal curve, and your t values go from 1.96 to 2.0 to 2.021 to 2.0245 to 2.056, 2.08, 2.12 at 16 degrees of freedom, at 11 degrees of freedom 2.2. As the sample size gets smaller and smaller, the t distribution gets fatter and flatter, and you have to multiply the standard error of the mean times a larger and larger value to have it honestly allow you to calculate the 95% confidence interval. So the 95% confidence interval for a normal curve, if you have samples of 150 to 200, whatever it would be, is 1.96 times the standard error of the mean. That's this range right here. Boom. The 95% confidence interval for a t-distribution with the sample size is only 12, you have to pull this baby out, and now it's 2.201 times the standard error of the mean. And so that's essentially the critical component of the critical role of sample size. So again, to sort of pull us out of this a little bit, confidence interval is a range-based estimate of central tendency of a hypothetical population based on a sample. Confidence intervals are always centered around the sample mean. This is true regardless of the sample size. For large samples, where n equals greater than 120, the range of values for the confidence intervals are based upon the standard error of the mean and the z-score. Again, the standard error of the mean is essentially an estimate of the standard deviation of the distribution of sample means. For smaller values, the range of values for the confidence interval is based upon the sample standard error of the mean, which you estimate from the sample, and the t-distribution values, which are associated with the hypothetical t-distribution of sample means. All that really translates to, all that really explains is why if the sample size is really big, a 95% confidence interval is the mean plus or minus 1.96 times the standard error of the mean from that sample. On the other hand, if the sample size is only 12, the 95% confidence interval will be equal to the standard error of the mean that you estimate from that sample times not 1.96, but the 2.201 that we saw in the t-table before. Because when there are 11 degrees of freedom, the distribution of sample means changes so that in order to capture 95% of those sample means, you have to go out 2.20 standard error units, not just 1.96. So this is what everybody's familiar with in terms of the math. If you have large samples, the 95% confidence interval is the 1.96 times the standard error of the mean, above and below that. If it's a 99% confidence interval, you use 2.56 times the standard error of the mean plus or minus. For the smaller samples, now you begin to have to bring in the t-distribution. And basically, it's the 95% confidence interval. It's the standard of the mean times the t-value at the appropriate degrees of freedom at the 95% level, the 0.05 cutoff, to the mean, and below and above the mean. And if it's the 99%, it's simply the standard of the mean times the appropriate t-value for that. Appreciate that as the reason that you cannot use just 1.96 when you have a sample size of 15, for example, is that the distribution of sample means when a sample size is only 15 is not normal. It is almost normal. It's the t-distribution of 14 degrees of freedom, which is, because of the work of Student, essentially we know that it's flatter, has a lower level for the mode, median, and mean, and it's fatter. A larger percentage of those sample means are out there in the wings, and in order to capture 95% of the distribution of sample means, you can't use the 1.96 value. You have to go all the way out to the 2.201 value. And that's the basis of using a t-distribution to calculate a confidence interval. The reality, of course, is that because the t-distribution at 120 degrees of freedom is essentially the 1.96, is the normal curve, this formula, this set of formulas here, the one that says it works for smaller samples and large samples too, that works for everything. In the real world, the 95% confidence interval is that range of values that is determined by the sample standard error of the mean, which is estimated from the standard deviation of the sample divided by the square root of n, times the appropriate t-value. One of those units below the mean and one above the mean. And that is, for any given sample, 95% likely to include the population mean. Again, the whole point of this is to go beyond simply saying, I have a sample, the mean is 125, so I think that the population mean might be 125, to I am 95% confident that the mean of the population from which I do this sample is in this range. And that range is calculated using the standard error of the mean estimated from your standard deviation of your sample times your t-value based upon your sample size. And that has to change because in reality, the distribution of sample means is a normal curve when the sample size is large. It's not a normal curve as the sample size gets smaller and smaller. From about 120 down to anything smaller than that, it gets closer and closer to being a fatter and flatter curve. And so in order to capture your 95%, you have to have a bigger and bigger window. So that's where we are. We've talked about normal curve. We've talked about the distribution of sample means and central limit theorem quite a bit. We talked about the standard of the mean and how it can be used. Theoretically, what it is derived from the distribution of sample means. Practically speaking, we calculate it in order to calculate a confidence interval. We use the sample standard deviation divided by the square root of n. We talked about the impact of different sample sizes and what the contribution of William Gossett, also known as student. And finally, confidence interval is a probability-based range estimate of the true population mean. It's always centered around the sample mean. It's calculated using the standard error of the mean, which you're using to estimate the standard the standard error, the sample means. And it's based upon the z-score from the normal curve or the z-score from the t distribution when the value is less than 120. And I think that's it. Thank you very much.